This video is about first-order logic. First-order logic is about predicates and quantifiers. A predicate is a statement about some unspecified objects that becomes true or false once those objects are specified. We can think about a predicate as something like a property an object could have, or a relationship between objects. We use uppercase letters for predicates and lowercase letters for variables representing the objects a predicate is about. For example, we could write p of x and y for the statement x can see y, which then becomes true or false when we specify x and y. We can make propositions by substituting objects for variables. For example, if we substitute u for x and me for y, then pxy becomes pu me, which means you can see me. We can also use logical operations. For example, p of u me and not p of me you means you can see me, but I cannot see you. The domain is the set of objects that we are considering. An interpretation is an assignment of true or false to each possible substitution of objects from a non-empty domain to variables of each predicate. As a domain for our predicate p of xy, we could choose Ada and Charles. Then, to make an interpretation, we choose a truth value for each substitution of Ada or Charles for x or y. In this example, Ada and Charles each see themselves, and Ada sees Charles, but Charles does not see Ada. First-order logic also involves quantifiers. We use two quantifiers: the universal quantifier, which looks like an upside-down A and corresponds to the English phrase for all, and the existential quantifier, which looks like a backwards E and corresponds to the phrase there exists. When we use quantifiers in a formula, we first write the quantifier, then a variable, then some formula that involves that variable. A variable appearing to the right of a quantifier is said to be bound in the formula, and any other variables not appearing next to a quantifier are said to be free. In this first example, x is a bound variable and y is a free variable. In this second example, both x and y are bound variables. For a formula phi of x where x is the only free variable in phi, and a given interpretation, we say the formula for all x phi of x is true when phi of x is true every time an object of the domain is substituted for x. Alternatively, we say the formula there exists x phi of x is true when there is an object in the domain that we can substitute for x to make phi of x true. An example of a problem we could have in first-order logic is to find an interpretation where a given formula is true and one where it is false. Consider the formula for all x, there exists y, there exists z, such that p of xy and not p of xz. Let's try to make an interpretation where this formula is true. First, we need to choose a domain. Let's choose the domain alpha and beta. To make an interpretation with this domain, we have to decide whether p of st is true for every possible substitution of s and t for objects in the domain. Since p is a predicate of two variables, we can represent p in a table like this, where the first variable is shown by the rows of the table and the second variable is shown by the columns of the table. Since x is universally quantified, we need the formula to be true no matter what we pick for x. And since y and z are existentially quantified, the formula only has to be true for some choice for y and z. So we have to choose truth values for p, so that whatever we choose for x, there's something we can choose for y that makes p of xy true, and something else we can choose for z that makes p of xz false. That means that true must appear in each row of the table, and false must also appear somewhere in each row of the table. With this interpretation, if x is set to alpha, we can make the formula true by setting y to alpha and z to beta. Alternatively, if x is set to beta, we can again make the formula true by setting y to alpha and z to beta. Now let's make an interpretation where this formula is false. One way we could do this is by choosing truth values for p so that some row of the table doesn't have false appear anywhere. In this interpretation, p of alpha alpha is true and p of alpha beta is also true. If we set the variable x to alpha, then there's no variable we can set z to that makes p of xz false. So that makes the entire formula false. Next, let's consider the formula in parentheses for all x p of x implies in parentheses there exists x q of x. Again, we need a domain, so let's choose alpha and beta. One way we could make this formula true is by making the formulas for all x p of x true, and also the formula there exists x q of x true. Again, we need to choose truth values for the predicates p and q for every value in the domain. To make for all x p of x true, we just make p of s always be true, whatever value we substitute for s. And to make the formula there exists x q of x true, we just need one value that we can substitute for s that makes q of s true. Now, since both for all x p of x is true and there exists x q of x is true, the whole formula evaluates to true implies true, which then evaluates to true. Now let's try to make an interpretation where this formula is false. To do so, we have to make for all x p of x true and there exists x q of x false. To make for all x p of x true, we set p of s to true for every value of s in the truth table for p, and to make there exists x q of x false, we set q of s to false for every value of s in the truth table for q. In this interpretation, the formula evaluates to true implies false, which evaluates to false.